All right, guys, so last section of our chapter 4 congruent triangle stuff. And I accidentally have an extra line here. I think I meant to separate the hints and then like flowchart proofs. Oh, well. So we're just going to do this one last topic, which is going to be that HL thing that we keep avoiding, which the HL thing is a theorem. And we're going to do that on page 51, but we're also going to like kind of go throughout and fill out some things that we haven't done yet. I almost just fell out on my chair. No biggie. So actually the first place that we encountered the little HL thing was right here. And so what HL stands for is hypotenuse leg. And the hypotenuse leg theorem states that if the hypotenuse, which is the longest side or the side opposite of a right angle in a right triangle, so if the hypotenuse and a leg, the leg is just another side, of one right triangle is congruent to the hypotenuse and the same leg of another right triangle, then the triangles are congruent. So you might be thinking like, well, why do they call it HL and not just something else? So if we kind of go through and mark what we have congruent here, we needed that the hypotenuses were congruent, which are the sides opposite your 90. We need a leg to be congruent and kind of the same leg on both. So like if I go with AC on the bottom here, I'd have to go with DF on the bottom there. And kind of the third thing that's kind of unspoken is that it has to be a right triangle, which I guess it's not really unspoken because if you have a hypotenuse, it's got to be a right triangle. So the last thing that we have is that I have to have this right angle making me a right triangle. So if you think about our three-letter shortcuts, what we have here is angle, side, side, which is not a good one. That's the bad one. But if angle, side, side happen to be on a right triangle, then you can use it, but we don't want to call it ASS because that's a bad word. So that's why we call it the HL theorem instead. And so we could say that the two triangles are congruent. So triangle ABC is congruent to triangle DEF. Okay, so we're kind of going through and filling out some of these old ones. Now, if we go to our triangles congruence proof book, we could use HL to now prove right triangles are congruent. And we skipped some of those examples in here on page 9 and 10. And so let's maybe do the one on page 9. So in my given, they tell me that QRS and TSR are right triangles. So I can kind of see in the picture that angle R is where the 90 is. And so that's what I'm kind of allowed to mark there, because if they tell me I have a right triangle, I for sure have a right angle in it. Now the other thing that's given to me is that QS is congruent to TS, which is super good because those are the hypotenuses of each of the triangles. But that's only two things, and I really do still need three things. So we have our right angle thing, we have our hypotenuse thing, so we need a leg thing. And I can use that reflexive property still in the middle and get that those legs are congruent. So when I go to do my squid proof, or my flowchart proof, I am using the HL theorem to prove that the two triangles are congruent. However, I still need three things, even though it's only 2 letters. I still need my 3 squid tentacles because it's really still angle, side, side, even though we don't call it that. So the first thing I want to say is that I have right triangles. So it's a little different because on these squid tentacles, I don't necessarily only put sides and angles. The first thing that I'm actually going to put is that triangle QSR and triangle TSR are right. And I know that they are right triangles because it was circle G given to me. The other thing that I need, so I have to have that they're right triangles, and if they don't give that to me, maybe they tell me that something is perpendicular, which then gives me a right angle, which makes them right triangles. So in that case, my squid tentacle would have a little bit more on it. But then I need that the hypotenuses are congruent, which are my pink lines. So QS was congruent to TS because that was circle G given to me, and those are our hypotenuses. And then I need a leg, so we said that SR was congruent to itself by the reflexive property. And I knew that I had that in the picture. And so then I could say that triangle QSR is congruent to triangle TSR by the HL theorem. Now, I wouldn't worry too much about proofs because we're not really going to do like a ton of HL proofs. So I'm going to skip the second one. And now I want to jump to page 51. So on page 51, we have our hypotenuse leg theorem notes. And really, when we look through this, we have that we're going to consider right triangles in the coordinate plane, which we've kind of already talked about. We talked about that last time. And proofs, which we literally just did. And then we want to look at it algebraically. So we're probably going to skip some of these because we've already done them a little bit. But if I take a look at this first one, we're going to just classify these triangles. I mean, we did that last time, but we can try one out. So if I take a look at this first example here, I would plot A at -2, -3. B is at 4, 5. So 1, 2, 3, 4. 1, 2, 3, 4, 5. And C is at 1, 2, 3, 4, 1, 2, 3. So yeah, when I take a look at this, that boy totally looks like a right triangle. But to know for sure, I have to figure out if I have a 90-degree angle in there or not. And it kind of looks like it's happening right here. And I feel like I know that it is because AC has a slope of 0. And BC, because it's vertical, has a slope of undefined. And so AC is perpendicular to BC, making it a right triangle. Now, I can also figure out if it's scalene, isosceles, or equilateral, because when the line is just horizontal like this, I can just count how long it is. So this is 1, 2, 3, 4, 5, 6 units long. And this is 1, 2, 3, 4, 5, 6, 7, 8 units long. And then I would have to do the Pythagorean theorem to get how long this one is, which is just going to be 6 squared plus 8 squared, and then square rooted. So 6 squared is 36, 8 squared is 64. When I add them up, it's 100. And the square root of that is 10. So now I can see that it is scalene. So maybe I'll skip that second one because we kind of did that yesterday or the other day. Now in proofs, again, the hypotenuse leg theorem says that we need to have a right triangle. So we got to have 3 things. We need a right triangle, hypotenuse, and leg. So in this quick example right here, which 2 triangles would be congruent by the HL theorem? Well, all 3 of them are right triangles, so that's not super helpful. But if I take a look, this guy has a hypotenuse of 5, and so does that one, but this last one doesn't. So these 2 would be congruent by HL, and that's because their hypotenuses and their legs are congruent. So I feel like we probably don't need to do this one here. I really wouldn't worry about it. If you guys want to do it, we can do it together tomorrow. The last one that I do want to do with you is how we use this algebraically. So if two right triangles are congruent by HL, then I can set their corresponding parts equal to each other. So in example 1 right here, this guy is the hypotenuse and so is that. So I can write the equation x equals 2y, which isn't super helpful because they got different letters. So maybe it'll be more helpful if I look at the legs. So this leg will be congruent to that one. Congruent means equal. So I can say that x minus 4 equals y plus 3. Not super helpful because that also has 2 letters in it. But maybe you remember from last year in Algebra 1 that I can solve equations with multiple letters in it if I have enough equations. So if I'm trying to solve for 2 different letters, as long as I have 2 equations, I can do it. And I do. And I also kind of know what x equals. X is equal to 2y. So really in place of x over here, I could put 2y instead because they're equal to each other. So I can like substitute it in. So if I do that, in place of x I put 2y, write the rest of my equation. Now I can solve for y. So I would get my y's together by moving the smaller one over. And because y will be over here, I'm going to also add the 4. And so I'll get that 1y is equal to 7. Now that I know that y is equal to 7, I can plug it in right here and get x, because that's going to be 2 times y, which I just found out is 7. So x is 14. Okay, so maybe we want to try another one like that. I'm going to skip. Am I? Nope, I'm going to do the one right next to it because I think the other ones are easier. But I might not do the other 2 right now. So if I take a look at this one here, I can set the hypotenuses equal to each other, which are these boys because they're across from the 90s. So if that's the case, I'm writing y plus 5 equals 2y minus x. Not great. I got x's and y's. Not great. But I can also write that my legs are equal to each other. So again, I'm going to like just get example 3 right out of there. Just ignore it. I need more space. I can write that y plus x equals x plus 7. It's also not great. It's got x's and y's. And I don't have like one letter by itself like I did last time. Like last time I just had this x alone, and so I could replace x with 2y, and I don't really have that here. Now I could move that y over, but then I'd still have an x and a y. If I take a look over here, ooh, actually this one's super good. I noticed that I have x's on both sides, so if I subtract this one, they're gone. So x minus x is 0. I have y left. X minus x is 0. That's it. Y is 7. So now I can, in place of y over here, put 7. Oh, I got another y, so put 7 again. And then I can solve for x. So I'm going to have 12 equals 14 minus x. Subtract my 14 on both sides and get negative 2 equals negative x. So x is 2. So kind of sneaky stuff, but if you can rearrange your equations and try to get a letter alone, you can do that substitution thing that maybe hopefully we will remember from last year. Now, just if we look at example 4 real quick, because maybe this stuff feels a little scary. If I take a look at my hypotenuses, that's not bad at all. And I can tell because they only have x's. So I can right now solve for x by subtracting x both sides and then subtracting the 1 to get that x is 2, which then helps me because when I'm about to go down here, like you do have x's and y's, but Now that I already know x is 2, I can just replace it. So instead of writing x plus y, I'm going to write 2 plus y equals this guy over here. And again, I'm going to replace this x with 2, so it's going to be 6 minus 3y. Then I can just get my y's together, so I'll add the 3y over for 4y and subtract the 2 over for 4. And so that means y would have to be 1. Alrighty, that's it. So we're going to go over this tomorrow, and then we'll have a test coming up here in a little bit, but we're going to review first, so no freakouts, and good luck.